Programming by example allows a user to provide 3 to 5 input-output pairs, which a synthesizer uses to infer a complex transformation rule. It is the automated logic behind spreadsheet autocomplete, data cleaning tools, and AI code assistance. This interface creates an immense lever. While the user provides a few rows, the resulting program is applied to millions of unseen downstream records. The model relies on implicit trust. Downstream users often accept these inferred transformations and apply them to entire databases without reading or auditing the underlying code. Because the training set is so small, the decision boundary is fragile. A single corrupted row can change the set of programs consistent with the specification. In PBE, a localized input error transforms into a systemic semantic failure that propagates across the entire data pipeline. Most robust PBE research focuses on natural human error. Engineers build synthesizers to tolerate independent noise, such as a user making a typo while entering an example. This defense targets stochastic expected loss. It assumes noise is drawn from a random, stable process, allowing the model to ignore occasional outliers. In a fixed set attack, the adversary identifies the specific edit that inflicts maximum damage. They aren't hoping for a random error. They are targeting the specific logic of the solver. Random typo evaluations miss this failure mode because they measure average case performance. Adversarial attacks instead find the worst-case maximization of error. True robustness requires mapping the exact geometry of the version space, identifying the algorithmic requirements for finding these attacks, and testing the limits of semantic aggregation. Optimizing for natural noise creates a blind spot, leaving live-inged meta transformation pipelines exposed to deterministic semantic manipulation. Consider a task extracting names. We have 2 inputs, Ada Lovelace to Ada, and Grace Hopper to Grace. These examples define a version space of candidate programs. The intended target program returns the first token. A rival returns the second. The stability of the synthesis depends on the disagreement margin. This counts the training examples where the target and rival program's outputs diverge. In this set, only the second row separates them. If an attacker changes the output of the second row to Hopper, both programs now satisfy exactly one training example. By changing enough outputs to match the rival, the adversary forces the synthesis to favor the wrong program based on its internal tie-breaking rules. This attack works because the corrupted row remains locally plausible to a human reviewer, while mathematically forcing the synthesis to choose the incorrect program. To test these vulnerabilities, researchers must simulate the adversary. However, the method of searching for these corruptions determines if the flaws are actually found. This 3D topographical map represents the search for an attack. Greedy, one-step search algorithms often fail on complex tasks. They take a single step, hit a flat plateau where no single edit improves the attack, and stop. This happens because a single edit might not immediately change the global ranking of the programs. You often need 2 or 3 coordinated edits to flip the synthesizer's decision. Finding the boundary requires a bounded exact search or a wide beam search. By evaluating multiple simultaneous edits, the search can traverse the plateau and discover the hidden vulnerability trench on the other side. Robustness evaluations that only use greedy attacks report false negatives. The absence of a greedy attack does not mean the system is secure. To defend the system, we can use Version-space Partition Aggregation, or VPA. This changes the decision from a single synthesis to a semantic vote. VPA first divides the training examples into completely disjoint independent groupings. The synthesizer runs independently on each group, generating a separate candidate program for every partition. Each candidate program is evaluated on a finite set of inputs to determine its functional behavior. This creates a standardized semantic signature for each program. The system then clusters identical signatures. A majority vote determines the final aggregated program. If each row only appears in one partition, an attacker with a limited budget can only flip a limited number of signatures. As long as the target semantics retain a majority of the votes, the defense recovers the correct program. We can measure this behavior empirically using generated tasks where the disagreement margin is exactly 1. In these trials, random typos have a 0 success rate, but a single strategic edit reaches 100% success, driving accuracy to 0. This requires a narrow margin. When examples are diverse with a high disagreement margin, the attack finds no damaging edits. Worst-case PBE corruption targets the mathematical boundary of the version space. It requires a low-margin region to succeed. While VPA works on controlled tasks, public benchmarks like the SciGus string transformations reveal its real-world limitations. In a 3-to-1 data split, VPA resists a budget 1 attack. Accuracy holds at 0.987. But if the adversary has a budget of 2 rows, they can control a partition majority. On these same tasks, VPA accuracy drops to 0.000. This failure happens because the clean vote margin on realistic tasks is often only 1. Adding a single extra edit to the adversary's budget allows them to overtake the majority vote. When the training set is small, there are only a few possible partitions. If an attacker's budget is large enough to control 2 out of 3 partitions, they control the final semantic vote, regardless of how those rows are randomized. VPA is a diagnostic tool, not a silver bullet. It provides a certificate of stability when votes agree with a margin, but it surfaces the ambiguity of the specification when that margin disappears. This vulnerability isn't limited to symbolic solvers. It also affects large language models using few-shot prompts. We see this across 6 major API models, including GPT and Claude. When subjected to a single example corruption in a prompt, their answer accuracy plummets from near 1.000 to 0.000. LLMs rely on the same high-leverage decision surfaces in their prompts. A single adversarial example produces the identical semantic collapse seen in symbolic synthesis. Low-margin inference tasks are inherently brittle. Securing them requires moving beyond average case noise tolerance and mathematically bounding the version space against a strategic adversary.